So, how does nanotechnology work? You can't see it even with a light microscope. And yet we're creating things with the realism of atoms and nanostructures. The nanotechnology itself is so new, most people aren't really sure where it even comes from. And yet, scientists are predicting that it will range in abilities from things like reproducing diamonds and food to the world to be devoured, and from like food to the world to be devoured by self-replicating nanobots. What we use to measure it with is nanometers, nm, which is 1/1000th of a meter, which is smaller than the wavelength of visible light and 100,000th the width of a human hair. Now, when you talk about material and elements that are this small in size, so refined, they act in a different way than much larger scales of these elements are by themselves, because of temperatures. Temperatures are very important when working with nanotechnology, because the temperatures affect how the elements interact with each other, and how you introduce them with each other at different temperatures will affect what you get. Let's put it this way: if you take carbon and you arrange it one way, you have diamonds. If you arrange it another way, that on this scale would be very simple, you have graphite. If you arrange them randomly, then you'll get soot. The nano way to arrange these atoms is to form them into tubes. And because they have such a small surface area with little layers of oxygen involved, the nanotechnology can then be utilized to, say, make a battery more efficient and yet keep it the same size. Imagine using a car battery to run an entire city. Scientists are currently working on some nanomaterial that can grow and repair themselves. Impossible, you might ask? These days, most creating or making of materials is by melting or molding them together. But in the nanotechnology world, you start with atoms and you start building them up and you start stacking them on top of each other in formation of however you want it to be. Sounds simple, right? And it is. And by doing this, you have an incredible amount of control. But how do we make it? I'm glad you asked. Using superconductors, which are metal and ceramic material that are found to have an electrical resistance of exactly 0, but it only happens at low temperatures of this substance. And using these superconductors broken down into thin sheets of metal, the beginning of nanotechnology reveals itself. But how to get the information that you need onto something that is so small that you can't see it to the naked eye requires very delicate machinery and various methods of stacking atoms that create a nanocrystalline thin film material. One of the most popular techniques is atomic layer disposition, which first requires the MBE method of preparing the superconducting thin films for the use of an electron beam that will sputter and flatten out and cause certain smoothness and ridges in the material. The MBE method takes a molecular beam that introduces elements to the oxide film that cause it to smooth out into 2-unit cells of a perfectly shaped thin film that is ready for the intrinsic factor of the atomic layer disposition. The intrinsic factor is a substance that is secreted from the gastric mucous membrane and is designed to absorb vitamin B12 in the intestines, and in the stomach it is used to develop parental cells that basically act as an element contributing to the production of results. That in this case, same thing. It helps introduce the elements. It's a catalyst, or an accelerator, if you will, that takes dangling bonds and starts surface reconstruction on the 10 films. And when I say films, I don't mean like TV. I mean like films, like films of metal sheets. This self-limiting deposition process that provides precise control of the composition of atoms separates precursor gases for like a target of material, acting in a sequential manner so that you can repeat data and then close it off in a vacuum so that you can put better computer control on the substance, so that basically easier way to work with it. Most of the chemicals used are aluminum oxide, hafnium oxide, zirconium oxide, and these types of material tend to I want to say grow, but they're easily stacked on and changed in low temperature conditions. Now, researchers have put substantial work invested into developing these ALD-like processes that yield high-quality films and use precursor gases, as opposed to previous forms of creating smaller technological structures, like evaporating films, or the CVD chemical vapor deposition, where creating patterns of dielectrics required subtractive processes in which whole layers were deposited, and creating these patterns was done by etching, which required much larger pieces of film, which is why using these new lasers we can work with smaller films. What else to say? I mean, to this day, we've gone way beyond Leonard Jones or Van D. Waals' discoveries. The photolithic ALD process started out with a centimeter scale of polished Si wafer with 1 um of thermally grown oxide that is cleaned for 5 minutes in each of the different chemicals that they needed it to be in, like trichloroethylene, which is a colorless poisonous liquid. So please do not try to drink any of the stuff that I mentioned. They are all dangerous chemicals. acetone and methanol, and then it is baked for 5 minutes at 160 degrees Celsius to drive off solvent resistances, like solvent residues. Then 1818 photoresin or something like that is spun into the sample, after which it is baked for 2 minutes at 120 degrees Celsius and is then exposed to a photomask, which is a machine that uses glass plates to integrate circuits, images of integrated circuits and information into chips or semiconductor wafers, which in this case is a film, a sort of microscopic wafer, and it is an important lithographic tool. In this situation, the photomask is larger than usual, where the patterns developed are using developed using tetramethylammonium hydroxide and cleaned for 30 seconds in an oxygen plasma chamber. And then, you know, the film needs a thin protective coating, a covering of sorts, before it is put into any sort of machine. For over 30 years, the work to miniaturize silicon transistors has been focused into computer technology, and shortly before, in 1965, Gordon Monroe, the creator of Monroe's Law, predicted that the trend in doubling the numbers of the amount of transistors on a single chip will increase every 18 months, and so far the prediction has been fairly true. And in 2003, President Bush signed the 21st Century Nanotechnology Research and Development Act, sponsored by Oregon Senate Ron Wyden, authorizing $3.7 billion for over 4 years of nano research and development that began in 2005. Since then, including the nanocrystalline metal sheets, there are also nano wires that are between 5 to 20 nanometers in diameter and only a few thousandths of millimeters long, that on a microscope, electron microscope, they resemble just a skinny little tiny thin needle, which they're making out of silicon now, which are used to integrate circuits that are also this small. The reason why it's not being utilized to current technology very much right now is because the methods to accomplish such feats are very, very expensive. The material itself is, in some cases, difficult to acquire, and they're trying to make better memory holding types of technology now, so in some cases the scientists work for very little. And the plan for these nanotechnologies is not to improve current existing products, but rather such technologies like aerogel, which basically is a non-melting material that is the byproduct of nanotechnology applications that will be used for space, transportation, construction, appliances, outdoor gear, sensors, air-water purifications systems. The aerogel is not like conventional foams that we use these days. But like foam, it has a lot of air in it. There's a lot of air particles in it. It's like 99.8% air. But it's a special material where the depository is on a micro scale, and it's composed of individual features that are only a few nanometers in size. They're going to use nanotechnology in cosmetics and personal care products, and we're not going to be using it to like enhance pills or anything, but we might be able to enhance the type of, instead of enhancing things, we might get new forms of surgery and new ways of making contact lenses that will be colored with a moisturizers of vitamin E. Basically, it's personal care. I mean, there are a few things that it is technically improving. I mean, contact lenses, but for the most part, there's going to be a lot of new jobs, a lot of new fields of degrees to have that people will have jobs for, thus bringing in more money. And little to our knowledge, there's a lot of products that we already use that have a form of nanotechnology involved in them. Sunscreens, they contain nano particles of zinc oxide and titanium oxide, which now allows the sunscreen to be more transparent. The older sunscreens, they used larger particles of these, so they are more clear, and that's why it's always white, like a whitish color, because they're using much larger particles. Well, now they've brought it down to a much more minuscule level, so it's a lot less visible. Self-cleaning glass, one of the products names is active glass, that uses nanoparticles to make the glass photocatalytic and hydrophilistic. The photocatalytic effect means that when UV radiation from the light hits the glass, the nanoparticles become energized and begin to break down and loosen organic molecules on the glass. And the hydrophilic it means that when water makes contact with the glass, it spreads across the glass evenly, which helps wash the glass clean. Some current day clothing have zinc oxide nanoparticles in them, which help protect us from UV radiation and helps repel water and other materials, making your clothes like less stain resistant and scratch resistant coatings for paper, because actually recently engineers discovered that adding aluminum silicate nanoparticles to scratch resistant polymer coatings made the coating more effective, increasing resistance to chipping and scratching. And it's commonly found in everyday things like cars and eyeglass lens. And even some of the antibacterial bandages have nanoparticles of silver in them that are used in the hospitals that help smooth out harmful cells that spread them apart, killing them. It's in swimming pool cleaners and disinfectants. During the past 40 years, computer technology itself has undergone many revelations of going through miniaturization of silicon transistors to approach nanotechnology, and even in December 2003, President Bush himself signed into law the 21st Century's Nanotechnology Research and Development Act, sponsored by Oregon Senate Ron Wyden, authorizing $3.7 billion for over 4 years of nanotechnology research and development that began in 2005.